All right. So we want to move into logarithmic functions. This is section 5.4. So I remember doing this content when I was in, Algebra 2. And then I never saw it again until I got to calculus. So I didn't see it for a few more years. Okay. So we want to define what is a logarithm. So a lot of students struggle with logarithms, but it turns out they're really just the reverse of exponential functions. We want to see that. So the idea is you have a positive number we're going to call a, and it's not equal to 1. So a is a positive number, and it's not equal to 1. We want to define what is the log base a of x. The log base a of x, well, it's a function, log base a of x, and we write it like this. Log, L-O-G, and then we put a subscript a, and then parentheses x. So we say f of x, our function, is log base a of x. Precisely when this double arrow here means precisely when a to the f of x equals x. So let's break that down. So we have a here, right? That's our subscript. So that's sometimes called the logarithmic base, right? Log base a. That becomes your exponential base, a. And then you make kind of a circle motion. You go a raised to the f of x power, right? This is the f of x power. And then you draw an arrow back to the x. So a, that's your base, raised to the f of x equals x. So it's really, a logarithm is just a different way of writing an exponential expression. So, for example, let's say I had just a real quick example. Rewrite the logarithm. A logarithm is just a fancy name for a logarithmic expression or logarithmic function in exponential form. So anytime you hear the word logarithm, that means a logarithmic function, oftentimes evaluated at a value. Let's say I had a log base 2 of 5 equals 32. So let's rewrite this in exponential form. So I'm going to start off with my base here of 2. Okay. And then I'm going to do this arrow. I'm going to draw it to the right-hand side. That's going to be my exponent here. The 3 is going to be my exponent. Oh, that should have been a 32. I don't know why I have a... Yeah. Well, let's just change something. That's fine. Let's make this an 8 right here. Let's make this one an 8, so it'll be a true statement. Okay, so log base 2 of 8 equals 3. Log base 2 of 8 equals 3. So we do 2 to the third power. And then from the 3, we're going to draw an arrow to the 8. So that's going to be our right-hand side of our equation. 2 to the third equals 8, which is a true statement. 2 to the third power is 8. Okay, let me draw another one out here. So we have log base 3 of, let's see, log base 3 of 81. Something I don't want to do later. Okay, equals 4. That's a true statement. So let's rewrite this in exponential form. So you start off here with your base, your log base becomes your exponential base. That's base 3. You draw an arrow from 3 to 4, so the 4 becomes your exponent. And then you draw an arrow from 4 to 81. So you put an equal sign, and after the equal sign, you're going to put your, that's called the argument, 81. 3 to the 4th power is equal to 81. So what's inside here, this green, what's inside the log is called the argument. Okay, let's do another. So I have log base 5 of, let's say, 1 over 625 equals negative 4. So if I wanted to rewrite this in its exponential form, I'd start off with the logarithmic base of 5 and write that as my exponential base. I can draw an arrow to the right-hand side, the minus 4, that's going to be my exponent. Negative 4, yes, you can have negative exponents. It is a thing. And we're going to put an equal sign, and then we're going to draw negative 4 and arrow to 1 over 625. That's our argument, 1 over 625. Now, this is a true statement. So I don't know how familiar you are with negative exponents, but it's an important skill to know how to use them. We teach that in our more basic algebra class. So a negative exponent means out front you have a 1. So we're going to keep the 1 on top. And you're going to take the 5 to the bottom. And the exponent of negative 4 becomes a positive 4. And that's actually equal to 1 over 625. Why? Because 5 to the 4th power is 5 times 5 times 5 times 5, which is 625. So yeah, that checks out. Okay, let's do one more. Just want to make sure it's one I'm not going to give you later down the road. Let's do log base 25 of 125 equals 3/2. So yeah, you can have fractions on the right-hand side of a log. Let's see how this works. So here I'm going to copy down, so we're writing it as an exponential. We're going to take the logarithmic base, make it the exponential base of 25. Draw an arrow here to the right-hand side. That's going to become your exponent, 3/2. And we're going to put an equal sign, and we're going to draw an arrow to the argument, which is 125. It's going to be our right-hand side, 125. Now, if you've ever dealt with fractional exponents before, you know that they are radicals, right? So the way you write this in radical form, it's 25. And then you take this bottom number here, the 2, and your fractional exponent. It's going to be the square root. And you take the top number here, the 3, that's going to be your exponent. So you're going to take the square root of 25 and then cube it. So again, the bottom number and your fractional exponent tells you you're taking a square root, and the top number, 3, tells you you're going to exponentiate by 3. If you actually think about this, first you do the square root of 25. The square root of 25 is 5, right? And then you would cube that, and you would in fact get 125. So it would check out. But this is how you write it in exponential form. I'm going to put them all in boxes, the exponential forms. So those are just the alternative forms to write the logs. Yeah, so we don't usually think in terms of logs naturally in our brains. So usually in our brains we tend to think in the exponential form. So it's good to be able to go back and forth between those two forms, from log to exponential and exponential to log. Now what else do I want to say about logarithmic and exponential form? Okay, so notation. Some notation. If you were to see this, log of x without a base, so in the past we always had like a number down here, an a, some number like 2 or something. So if you don't see a base down there, this means log base 10. It's understood to be base 10 automatically. Okay? Now another important notation, if you see a ln, that's called the natural log. The natural log. This is log base e. Log base e. So e is a number that's approximately 2.718. It's a very important number, e. It shows up a lot in nature. It has to do with growth and decay of things. So be familiar with those two notations. Log without a base is log base 10, and ln, natural log, is log base e, where e is a very special number. Okay. So what we want to do, we want to get around to evaluating logarithmic expressions. So I have a logarithmic function, log base 2 of x. In place of the x, in place of the argument, the input is called the argument, I want to put 32. So what is log base 2 of 32? We want to figure that out. So I'm going to start this here. I'm going to write here, this is equal to y. Okay, it's equal to y. I'm going to write the exponential form of this. I'm going to write down a 2, so I'm going to have 2. Okay, this should be blue, I guess. Let's make it blue. 2 to the y power equals 32. So what can I raise 2 to what power to get 32? 2 to the what power gives me 32? It turns out 2 to the 5th power, right? All right, if I multiply 2 together 5 times 2 times 2 times 2 times 2 times 2, I'll get 32. So the answer is log base 2 of 32 is 5. Okay, number 2. I'm going to have log base 6 of 216. I want to evaluate log base 6 at the input, 216. So my x value is 216. I want to find my y value. So I'm going to set this equal to my y. I don't know what my y value is. I'm going to start with the exponential base of 6. So we're going to have 6 to the y power equals 216. And if you think about that long enough, you'll figure out that y here is 3. If I multiply together 6 3 times, I'll get 216. 6 times 6 times 6, 216. So the answer here is log base 6 of 216 is 3. Okay, let's do a number, I'll do a number 3 up here. So I have log base 64 of 8. I want to find what that is. Well, we're going to set it equal to y first. And we're going to write down our logarithmic base, which is 64. We're going to make it an exponential base of 64. So we're going to take 64 to the yth power. And we're going to say that equals our argument 8. Now this is where it gets tricky. So what can we raise 64 to get 8? Well, some of you that are familiar with fractional exponents will know that answer really quickly. But if you're not really good with fractional exponents, what you can do is try to get 64 and 8, rewrite those in terms of a common exponential base. So you can write these both in terms of 2 to a power. For example, 64 you can write as 2 to the 6th power. So I'm going to rewrite 64 as 2 to the 6th power. I'm going to put that in parentheses and put a y out top. And I can also write 8 in terms of exponential base 2, that's 2 to the 3rd power. So they both are 2 to some power, right? 64 is 2 to the 6th power. 8 is 2 to the 3rd power. Now I'm going to use my properties of exponents. I'm going to take here 6 times y there. That's the way you do that. So we're going to have 2 raised to the 6y equals 2 raised to the 3rd And now we're going to take our exponents, the 6y and the 3, and we're going to set them equal to each other. So we're going to have 6y equals 3. And to get y by itself, we divide both sides by 6. The 6's cancel on the left, and you get y is 3/2. I'm sorry, 1/2. Saying it wrong. So 3 over 6 reduces to 1/2. So your answer here is that y is 1/2. Now let's actually think about that. Let's actually check this one. So we have, let's see, if I go back to my second line here where I'm putting a box around, that means 64 to the 1/2 power equals 8. Is that true? Well, what does it mean to raise 64 to the 1/2 power? Well, you have a fractional exponent. So remember, you take the bottom of the fractional exponent, which is 2. That's going to be your root. It's going to be a square root of 64. Then you're going to put parentheses around that, and then you're going to take your top of your exponent. That's the numerator of the exponent, 1, and you're going to raise it to the 1 power. Is that equal to 8? Well, let's see. You take the square root of 64, which is 8, and you raise that to the 1 power, and that's 8. So yeah, it checks out. So you don't have to check your work, but sometimes it's useful, especially if you're just beginning. You can understand these fractional exponents. Yeah, so fractional exponents are a little tricky. Also, you'll encounter some negative exponents, which sometimes are a little tricky for people that aren't really that familiar with them. So let's do one log base 3 of 1 over 81. So we want to evaluate log base 3 at 1 over 81. So let's call it y. So we're going to take our logarithmic base 3 and make it an exponential base 3. And we say we have 3 to the y power equals 1 over 81. Okay? Now, some of you maybe are good with negative exponents. If you're not, though, you won't just know the answer to this off the top of your head. So what you want to do, for now, we're going to leave 3 alone and y alone. And we want to think about rewriting the right-hand side in terms of a power of 3. Well, first of all, I'm going to leave the 1 on top, and think about 81. 81 to what power? I'm sorry, 3 to what power would give you 81? 3 to what power? If you want to think about a base 3, since the left-hand side has a base 3, you would want a base 3 on your right-hand side. So 3 to what power would give you 81? Well, 3 to the 4th power is 81, right? So we have 1 over 3 to the 4th. 1 over 3 to the 4th. So on the left side, we have 3 to the y. And on the right side, we have, 1 over 3 to the 4th is the same thing as 3 to the negative 4th. Yeah, so that's where the negative exponent comes into play. So when you have something on bottom, you can take it up top and make the exponent negative. So now basically, we have a y here that matches up with a negative 4, so we can set those equal. So we get y equals a negative 4 power. And that's your final answer here. Yeah, so if you want to go back and check this, let's look here in the red box. If I wanted to check that. 3 to the negative 4 power equals 1 over 81. Is that true? Well, remember what 3 to the negative 4 means. It means you're going to take, imagine there's a 1 out front here. You're going to keep a 1 on top. You're going to take 3 to the bottom and make it a positive 4 exponent. Is that equal to 1 over 81? Yeah, right, because 3 to the 4 here on bottom that I'm circling is 81 exactly. So it checks. Okay. So you don't have to check your work, but it's nice sometimes when you're just starting out. Let's do a number 5. Let's say we have log base 8 of 1/2. So we want to find out what that's equal to. Let's call it y. So I'm going to take the log base 8, the base 8, make it exponential base 8. And raise that to the yth power. That's going to be equal to 1/2. Okay. So this is a little tricky. So if I look at this number here, 8, where'd it go? It disappeared on me. 8. If I look at this number 8 and this number 2, we want to think about maybe a common exponential base. They both can be written as exponents as 2 to some power. So I'm going to rewrite, first of all, be 8. 2 to some power. How can you write 8 as 2 to some power? Well, you can write it as 2 to the 3rd power, right? 2 to the 3rd power is 8. Then I have a y here. Now on the right-hand side, I want to think about, so this is on the bottom, this is 2 to the 1 power on bottom, right? 2 is just 2 to the 1 power. But I want to think about how can I rewrite that so that it's up top. Well, I can rewrite the right-hand side as 2 to the negative 1 power, right? If I have 1 on top and 2 to the 1 on bottom, I can take the 2 to the 1 up top and it becomes 2 to the negative 1. Now, on the other side of the equation, the left side, what we can do is multiply the 3 and the y using your property of exponents. You get 2 raised to the 3 times y. So what we're going to do, we're going to set the 3y equal to the negative 1 now, since everything matches. We have 2 to some power and 2 to some power. So we set 3y equal to negative 1 and divide both sides by 3. 3's cancel on the left, and you have y equals minus 1 over 3. So your exponent is minus 1 over 3. Oh, your logarithm. Logarithm is minus 1 over 3. Now, if you wanted to check that, you don't have to check these, but let's check it. So I'm going to go back to the step I put in the black box. I have 8 to the minus 1/3 equals 1/2. Let's see if it checks. Well, what does 8 to the minus 1/3 mean? First of all, think about the negative power. The negative power means you're going to keep a 1, which is out front here, on top. And you're going to take 8 to the positive 1/3 to the bottom. So you make that negative 1/3 a positive 1/3 on bottom. Now let's do 8 to the 1/3 power. What does that mean, 8 to the 1/3 power? So the 1/3 power means you're going to take 8, and the 3 on bottom of the fractional power means you take the cube root, and then the 1 on top of the fractional power means you raise it to the 1 power. So on bottom here on the left side, I'm going to take the cube root of 8. What's the cube root of 8? Well, it's 2, right? And then we're going to raise it to the 1 power. Is 2 to the 1 power 2? Yeah, it is. So you get 1/2 equals 1/2. So it checks out. Okay, so our answer was minus 1/3 for that logarithm. Let's do a number 6. I have log base 25 of 125. Log base 25 of 125. So we're going to call this y. And I'm going to write down my logarithmic base as my exponential base. It's going to be called 25. I'm going to raise that to the yth power, and that's going to be equal to 125. Now I want to think this 25 on the left-hand side and this 125 on the right-hand side, do they have a common base, common exponential base? They both can be written as 5 to some power. So 25 can be written as 5 squared, so I have 5 squared in parentheses, raised to the yth power. And on the right-hand side, the 125 can be written as 5 cubed. So using our properties of exponents, we can multiply the 2 here in the y. We have 5 raised to the 2 times y equals, and on the right-hand side, we'll have 5 raised to the 3rd power. So since they're both in terms of base 5, we can set the 2y equal to 3. So 2y equals 3. Divide both sides by 2 here. The 2's cancel on the left, and you get y is 3/2. Yeah, so our answer for this logarithm is log base 25 of 125 is exactly 3/2. So you want to show your work on this. You don't want to just plug this in a calculator. So you can always check your work in a calculator for, it depends on your calculator, of course, but I want to see the work. I want to see that you know how to rewrite these as exponentials and then solve these exponential equations. Okay, we'll do one more. Number 7. What happened there? Okay, log base 16 of 1/8. So I'm going to call this y. I don't know what it's equal to, so I'm going to call it y. Now I'm going to rewrite this in exponential form. I'm going to write down the 16 as the exponential base. 16 gets raised to the yth power. And that's going to be set equal to the argument, which is 1/8. Now we want to try to rewrite the 16 and the 8 in terms of a common exponential base. So 16 I can think of as at 2 to some power. 16 is what? 2 to the 4th power. So we get 2 to the 4th power raised to the yth power. And 1/8, we can think about the 8 on bottom as 2 to the 3rd power. 2 to the 3rd power. Now on the left side, I can multiply the 4 and the y using properties of exponents to get 2 raised to the 4 times y. And on the right side, I can rewrite my fractional expression as 2 to the negative 3rd power, right? When you have a fraction like that, when you have a 2 to the 3 that's on bottom, you can take that up top and it becomes 2 to the negative 3. So we set our exponents equal to each other now that they're both in terms of base 2. We set 4y equal to negative 3, and we divide both sides by 4. The 4's cancel on the left, and we get y equals minus 3/4. So our answer here is minus 3/4. All right, I think we'll stop evaluating. No, we'll do one more. One more I want to do that's special. This will be number 8. This will be the, no, I don't want to do one more. I want to do a few more. ln, remember ln is the natural log of e raised to the 2021. So this is called y. Let's set it equal to y. We don't know what it is yet. So remember what this is. When I see natural log, that means log base e. So I'm going to rewrite this. Log with a base e. And then inside of the argument, we have this green stuff, e raised to the 2021 equals y. So the first thing I did, I rewrote the natural log as a log base e. Okay, so after I've rewritten that in terms of the log base e, I can now put it in exponential form. I'm going to start off with the base e as my exponential base. So I have e raised to the y power. And then this is going to be equal to e to the 2021. So these are both in terms of base e, so I can set the y equal to 2021, and I get y equals 2021. So that's my answer, 2021. Okay, that's a nice little problem. Let's do a number 9. This one's going to be log of 1 over 1 million. Now, first of all, let's rewrite this. So let's call it y. Before we write it in exponential form, let's rewrite it in logarithmic form. The question is, when you just see log without a number here, right, you don't have a number here down at the bottom, that's understood to be what? Log base 10. So let's write as log base 10 of 1 over a million. Oh, that's a billion. I'm sorry, that's a billion, not a million. 1, 2, 3. They're 9 zeros. They're not 6. So it's a billion. All right, so now we're going to put it in exponential form. We're going to start with the 10 as the exponential base. 10 raised to the yth power. Equals 1 over a billion, 1 billionth. So we want these both in terms of a similar base. So I think base 10 is good already. So we're going to leave on the left side 10 to the y. And on the right side, we're going to think about a billion. A billion. So I'm going to leave the 1 on top. And for now, I'm going to leave the 1 on top. And on the bottom, I'm going to say, what's a billion? It's 10 to the 9th power, right? 10 to the 9th power is a billion. Because there are 9 zeros. When there are 9 zeros, that means 10 to the 9th power. So then we're going to rewrite this so that everything's on top. So on the right side, I'm going to rewrite 1 over 10 to the 9th power as 10 to the negative 9th power. Right? When you have something on bottom, you can take it up top and make the exponent negative. So now I can just match up my exponents, y and negative 9, so I get y is negative 9. That's my answer there. Negative 9. Okay, and maybe just one more problem I want to focus in on. Number 10. Number 10 is log base 7 of negative 343. Okay, so we'll set this equal to y like we've been doing. We'll rewrite this in exponential form where we have exponential base 7 raised to the yth power equals the argument negative 343. Now, if you think about that and try stuff for long enough, you'll never get an answer. There'll be no solution. I'm going to tell you up front, there's no solution here. And the reason there's no solution is because you can never take something and raise it to a power and get a negative number. So this green dude right here, it's impossible to raise something to a power and get a negative number. Think about it. If I take 7 and raise it to the first power, I get 7. 7 to the second power, I get 49. 7 to the third power, I get 343. So those are all positive, right? These are all positive. Now let's try like 7 to the 0 power. Well, 7 to the 0 power is 1. That's still positive. Let's try 7 to the negative 1 power. That's 1/7, which is positive. Let's try 7 to the negative 2 power. That's 1 over 7 squared, or 1 over 49. Still positive. If I take 7 to the negative 3, that's 1 over 7 cubed. That's 1 over, well, 7 cubed is 343. That's still positive, right? They're fractions, but they're all positive. So 7 to a power is always going to be positive. So it's impossible. It's absolutely impossible to raise 7 to a power and get a negative number. So the key here is that what's inside of the argument, what's in green here, should be circling in green. Come on, green, work. That always has to be positive. So here's an important fact. The argument of a logarithm, which we sometimes just call log, I'll say a logarithmic function must be positive. Very important. Yeah, so as soon as I have a negative argument here, like negative 343, I know it's undefined, so there's no solution. Or let's say it's undefined here. Undefined is a better way to say this. Undefined. You can say no solution as well, but undefined